Yeah, the next speaker is Jim Halverson from Northeastern University. He's going to tell us about deep learning landscapes. And Jim, I will give a warning after 25 minutes. Yeah, please.
I just realized I am muted and my video is not on, which makes it very difficult to give a talk. Thank you for the introduction, Babu, and thanks to the organizers for the invitation to speak at this wonderful conference. So the title of my talk is Deep Learning Landscapes. So I'm a string theorist, but one who cares deeply about particle physics and cosmology. And like many string theorists, I also work in areas related to pure math. And increasingly, I'm interested in deep learning, as are many of you. And so what I'd like to try to do in this talk is to tell you a little bit about how all of these ideas can fit together. And in particular, this is not just a talk about deep learning for the landscape of string vacua. Landscapes has an S here, and that's part of the point, is that when we talk about landscapes generally and ways that one might use deep learning in them, from a 10,000 foot view, if you just go to Google and you go to the images section and you type in string theory landscape, what you end up with is lots of different pictures, but these are the sorts of pictures that we have in mind when we think of the string theory landscape. So in this case, this sort of picture would be representative of an effective potential on some space of scalar fields coming from a string theory compactification. And it has many metastable minima, which are corresponding to vacua that are metastable in theory. And there's a question of sort of which one would be ours. But landscapes are more general than that. And in particular, without even thinking about applications of deep learning to physics, deep learning has its own landscapes. And if you Google, deep learning loss landscape instead of string theory landscape, you end up with very similar looking pictures, where the analog of the effective potential here is the loss function on the space of parameters in deep learning. And these questions emerge in both cases, which is, what happens if you get stuck for a little while, and how might the dynamics of the system naturally drive you to lower energy minima, which in deep learning would make better predictions, and in string theory would do something like correspond to smaller cosmological constants. But this phenomenon is actually much more general. So landscapes show up throughout the sciences. So a hat tip at frustrated spin glasses and protein folding are in order. And this phenomena is characterized by sort of energy functionals that have many metastable minima, and the dynamics of those systems are difficult to understand. So landscapes are ubiquitous, they're important, and they're hard. But so how does all of this sort of fit into this usual story that we're used to, that math and physics belong together in some sense? And this goes back thousands of years. And here are some recent applications that have come up in our communities. This is sort of the question. We have on one hand these new breakthroughs in computer science. On the other hand, we have this long-standing story about how math and physics fit together. And Wigner has this quote about the unreasonable effectiveness of mathematics and the natural sciences. But the question sort of arises, are we moving in a direction where computer science is becoming a third vertex of this interplay? And are we moving in places where we're starting to see computer science affect math and physics in the way that they have traditionally affected each other? So computer science is the new kid in town, and certainly in the string theory community, there's increasing interest in both deep learning and in quantum information. I don't have anything to say about quantum information today, but this is sort of one of the things that we see starting to happen in our communities. So in particular, a lot of my career is sort of spent living in this area. And one part of the talk today is going to be, how does the mathematics of string theory affect how we think about the physics that arises out of it? But on the other hand, we're going to see that physics also affects computer science, and that'll be the other half of my talk. So if you're interested in this area, there's many ways to connect at the interface of physics and machine learning. I encourage you to check them out. In particular, we are wonderfully fortunate to have support from the National Science Foundation for the recently started Institute for Artificial Intelligence and Fundamental Interactions. This is one of 5 new AI research institutes that the NSF has started up. And this is the one at the interface with physics. So I'm one of the co-PIs on this, but we also have colleagues at MIT, Harvard, and Tufts involved. And there's a lot of things to say about this, but sort of the essence of it, for me at least, is can machine learning help for physics and math discoveries? And also, can physics and math help machine learning? Another thing you might want to check out is we have a virtual seminar series running for a year now that is a follow-up to a meeting that we had at Microsoft Research in 2019. And if you're still interested beyond those, feel free to just contact me directly. I'm happy to try to give you interesting references. Okay, so this is PHENO 2021 though, and so I want to do my best job to focus on the PHENO aspects of these subjects. And in particular, the questions I want to ask are, given that string phenomenology and the string landscape have been things that we've known about for a while, what are some of the best takeaways from the string landscape in 2021 that might affect how we think about particle physics and cosmology? And in particular, can we use phenomenology to the second part of the talk is, can we use phenomenology in some sense to understand neural networks? And I'm casting a broader net of what phenomenology means there, in the same way that a condensed matter theorist might say that they're doing phenomenology of some condensed matter system. We want to ask, can we also do phenomenology of neural networks? And the unifying framework when we talk about particle physics and cosmology and condensed matter physics all having phenomenology is quantum field theory. So quantum field theory phenomenology can be applied to many different systems. And in particular, we want to try to do that with neural networks as well. Okay, so I have two main points in this talk, and I'll tell you what they are right away, and I'll revisit them at the end. The first is that when we think about string phenomenology in 2021, one of the takeaways is if you take the broadest set of string constructions we possibly know about, and you draw vacua from a uniform distribution on those known string constructions, what we find is that there's many string remnants, new degrees of freedom that arise from the UV that might not be there to solve any low energy phenomenological problem. So these could be many axion-like particles, many gauge sectors, and in particular, new results from the last few years suggest that these are light and weakly coupled when the theory is under control. So these potentially detectable remnant degrees of freedom are everywhere, and this gives rise to both problems and opportunities for string phenomenology. And the second part is neural network phenomenology, a phrase that I have never used until this conference, but in particular, I think that this is what this is, and so I'll try to explain that. The takeaway is that neural networks themselves are random functions, and the key insight is that they're random functions from nearly Gaussian distributions on function space, and that's like what happens in particle physics. So in particular, many times when we're doing phenomenology, we're modeling the non-Gaussianities in the action to try to describe some weakly interacting system. And one result that I'll talk about is how you can use duality to determine the symmetries of those systems. Okay, so string phenomenology in 2021, I want to give you a broad view of what we know about the string landscape. The string landscape is part of string theory, of course, which is a quantum theory of gravity. It is a candidate theory of everything. It can give rise to semi-realistic particle physics and cosmology. And one of the central aspects in string theory is that it has extra dimensions. And so what we need to do is to compactify those to end up with some low energy effective theory. And crucially, the geometry and the topology determine aspects of the four-dimensional physics, the geometry and the topology of those extra dimensions. So think of this on that little triangle I gave you. This is the math to physics direction. And so there's this question of, based on what we know about the geometry and topology of the potential extra dimensions in string theory, what do we learn about the four-dimensional physics? Crucially, there are many, many, many ways to do this. Here are some large numbers that I'll have more to say about. And collectively, these many solutions or vacua of the theory are referred to as the string landscape. A question quickly emerges if you have many vacua, or alternatively in other landscapes like in deep learning or protein folding, there's a question of what is the dynamics and how does the dynamics on that landscape choose particular types of metastable states over others perhaps, or does it choose many of them? And this arises in string theory via bubble nucleation. Bubble nucleation starts with one vacuum and then it produces another vacuum within it via for instance, Coleman-DeLucia tunneling. And concretely what it means is that predictions in string theory are statistical. I have nothing to say about anthropics today, but crucially, dynamics affect these statistics in important ways. And that's one thing we would love to know. If we had perfect knowledge, what we might end up with is some distribution on string vacua that allows us to make concrete statistical predictions. Okay, but we don't know the right distribution on vacua. So as a proxy for that, what I want to do is ask if we drew vacua from a uniform distribution, given what we know in 2021, what would we find? And of course, the caveat is that the broader that we go in the string landscape, the fewer details are worked out. So you should think of, as we go broader, think of this as an impressionistic first step of an analysis, rather than high resolution photos where you did every single calculation you could possibly do. So let me tell you about the largest ensemble of concrete visible sectors. So there is a paper that has the title Quadrillion Standard Models in the title. And in the PHENO community, I should really put standard models in quotes. What we mean here is that in this context, we have a picture like this, where these points can be triangulated. This produces an extra dimensional configuration in string theory of a particular type. And you can do this in a very controlled way in 10 to the 15 provably distinct ways. And in those contexts, what we have is a fully consistent compactification of a type of string theory called F theory with the exact chiral spectrum of the minimal supersymmetric standard model. So getting to that point in a string construction is actually pretty difficult historically, but this is the largest existing ensemble of concrete visible sectors. But crucially, they're constrained. So in this ensemble, the following cannot all be true: that our vacuum with the correct values of the standard model gauge couplings lives in this or a related ensemble. Second of all, the theory is controlled. And third of all, there's no additional dark sectors on 7 branes. So if you want to have a vacuum in this ensemble with the correct gauge couplings, you have to pick one of these two, either that you can control the theory or there's no dark sectors on 7 branes. So this is one example of the sort of thing that happens in concrete landscape studies, which is that there's no free lunch. You can't just do whatever you want. There are correlations in the data that comes from string theory, in the theoretical data. And so you can't just tune the string EFTs at will to whatever you want. Okay. But that's not my main point. My main point when it comes to landscapes is that when we look as broadly as possible, it's a big world out there. The largest, I think it's safe to say that the largest part of the landscape that we understand currently is in something called F theory. And there's a result from 2015 of Taylor and Wang that claims to, and I think they did it correctly, have identified the extra dimensions of string theory that gives rise to the largest number of flux vacua. So this is from precision knowledge of a structure called an elliptically fibered Calabi fourfold. We think we know the geometry with the most flux vacua in that case, and the number that they give is this, which is notably much, much bigger than the 10 to the 500 that you might traditionally hear. So, right, concretely, even though there's a very, very large number of these, before you turn on potential flux breaking, there's a universal structure that arises in these flux vacua, which is a very large gauge group with this structure. There's also many axion-like particles. And so what it gives rise to is a complicated cosmology with many degrees of freedom that no one ordered, but nonetheless can have important consequences. That's the geometry with the most flux vacua. Instead of going that direction, you can say, what if I just construct the largest ensemble of geometries that I possibly can? I cited this title here of our paper because the title has a point. We actually have a concrete construction algorithm that, given a sufficiently strong computer, would be able to construct 10 to the 755 fully consistent, sorry, I should back off that a little bit, actual compact Calabi manifolds that are connected to one another via topological transitions, and each of them is topologically distinct. And we can actually, even though we never construct all 10 to the 755 elements of that set, what we can do is draw from a uniform distribution on that set and ask what sorts of things do we see on average in this large ensemble of geometries. And the thing that we see is that we have 750 gauge sectors on average, or something like that, you just can't get rid of. And we have many, many axion-like particles. In particular, the expectation value is in the thousands when you draw from this uniform distribution. So these are complicated cosmologies, and different people might have different takes, but I think one takeaway from 35 years of string phenomenology, given everything that we know about the string landscape, is that there are string remnants. So string remnants is my collaborator Paul Hangeker's phrase that he impressed upon me at some point. And what we mean by it is that these are new degrees of freedom that are apparently accidental consequences of the UV theory. These are degrees of freedom that show up. They are not motivated by shortcomings of the standard models of particle physics or cosmology in general. So it's different than the normal model building paradigm. And there's many things that arise. And I encourage you, if you're interested, to look at my TASI lectures from a few years ago. There's all sorts of things that one has to consider seriously. Another result since then is that there are implications that come from considering control in this context. So a result out of the Cornell group a few years ago pointed out, well, they didn't point this out, generic vacua arise at large number of topological cycles. That's where most of the vacua in the landscape are expected to live. And one thing that happens, and this is their result, is that when you're in that situation where the topology of your extra dimensions is very complicated, if you demand control of the theory via having a supergravity approximation, what happens is that you get pushed out in the space of scalar field expectation values such that the remnants become more and more important. So this getting pushed out in the stretched Kähler cone in the lingo generally gives you increasingly light axion-like particles and weaker gauge couplings, which means, depending on which experiments you're looking at, these remnants are becoming more important. And so I want to give you one example. This is one thing that I really have enjoyed the last few years. I think with this sort of thinking about the string landscape, there's all sorts of things that you have to take into account in particle physics and cosmology. But what I want to talk about is ALP-photon couplings. So I think this is a model narrative for how you might think about particle physics and cosmology differently, given what we know about string theory. So the goal is to land at some well-motivated ideas for PHENO from the string theory perspective. And so I just want to make the following points. If string theory is true, it has to have a photon, yeah? And yet when that's true, and when we study string theory as broadly as possible, axion-like particles are sort of all over the place. The number of ALPs, n, is large. And in particular, due to this result from the Cornell group, in cases that we can control, those ALPs are going to be particularly light. And finally, there's no symmetry that forbids those many ALPs from coupling to the photon in the effective field theory. And so there's this question that emerges: how does the axion-like particle photon coupling coming from the dimension 5 operator, A, F, wedge F, how does that scale with n in the landscape? Given that we think that large n is where most of the landscape lives, we would love to know how this coupling, which is probed by experiments, scales with n. And we had a paper that did this a few years ago in a toy model. Part of the reason that I think the ALP-photon story from a string perspective is so exciting is that it's so concrete. But the other reason that it's so exciting is that there's really good experiments coming from axion helioscopes and also from X-ray satellites. And basically, in terms of the axion-like particle coupling, we're only a few orders of magnitude off from 1/gut. And so these are very, very sensitive experiments that are only getting better. And the question that we were sort of interested in, if Planck scales down here, as you increase n in the string landscape, is the distribution in this toy model pushing the expectation value of GA gamma gamma to higher and higher values? And this is what we found. So this is just one example, but the basic punchline is that we should be taking these remnants that come out of string theory. If we want to do string phenomenology and cosmology, we should be taking them very seriously because they can have observable consequences. Okay, so that's part one of my talk. Part two is very different. This is sort of, instead of thinking of what does the math of string theory imply about particle physics and cosmology, I want to ask what does physics have to say about computer science, which is sort of bringing these different stories together. And in particular, I want to talk about what I'm calling neural network phenomenology for the first time. What I want to try to convince you, and this, I probably just told you some stories that you may be familiar with from previous talks you've heard. For many of you, this story might be new, so I'll try to explain it as clearly as I can. So my claim is that there's a deep relationship between neural networks and quantum field theory. And if that's true, then some of the techniques that we use in quantum field theory phenomenology might be applicable to understanding neural networks better, which could be important and open up avenues in theoretical machine learning. This is based on work from last summer and also work to appear this week, both with my wonderful students, Anandita and Kike. So to remind you, the linchpin of what is happening in this revolution in deep learning is neural networks. There's different types of deep learning algorithms, but neural networks are central to all of them. So the standard ones that you might be familiar with are supervised learning, where you learn to predict that that's a 3, that that's a 3, that that's a 3, and that that's a 3. You learn to predict outputs given inputs. But there's other types of ways in which neural networks are used in deep learning that are fundamentally different. There's reinforcement learning, which leads to world-leading programs in Go and chess. There's something called natural language processing that has these famous results from last summer, where you can fill in a little bit of a prompt and the AI will, the neural network will complete the prompt into some paragraph of text that is readable and interesting. And I think that this is an amazing result. This is something called a generative model. A generative model is a neural network that takes in noise, some draw from some simple distribution like a multivariate Gaussian, And after training, it produces some draw from some target data distribution, where here it's sort of the distribution on human faces. The point here is that this person, who looks very convincing, if I showed you her in a lineup, you would not be able to pick out that she's fake. But indeed, this person does not actually exist. This is an image that's generated by a neural network. And these sorts of generative models are starting to make their way into particle physics and string theory and other aspects of physics. But those are just some of the ways that neural networks show up. My point is that neural networks are powerful functions. That's really what we need for this talk. So a neural network is a function from some input dimension space to some output dimension space. You can vary the domain and the range if you want. Crucially, there are continuous learnable parameters theta and a discrete hyperparameter n that I'm going to talk about. And in these examples that I just showed you, the training procedure by which neural networks are optimized updates these parameters to improve the performance for whatever it is that it's trying to do. But crucial for today is to remember that these parameters are drawn from some distribution over parameters. Parameters are random variables, and a concrete neural network on your computer has parameters that themselves are draws from that distribution. So if you fire up your code and you have it create a neural network, those parameters are drawn from some distribution and slotted into some sub-functions that you compose in particular ways. But very concretely, overall, this neural network is just a random function. Okay. But what if you restart your code? What if you do it again? Well, it draws the parameters again, and you're going to generally get different parameter draws. And so it's a different random function. And since I quoted you large numbers like 10 to the 755 and 10 to the 272,000, imagine that you restarted your code that number of times, again and again and again. You're going to get all different neural networks, all different random functions. And the point is, when we think about these random functions associated with these neural networks that we initialize, we have to ask random functions from what distribution? So normally we think of neural networks as having an architecture with random parameters, but as I've just emphasized, we can also think about them as random functions, and we should ask questions about them and study them from the perspective of function space. And this is the crucial point that I'm going to make in the rest of my talk. So this is a fine thing to say, that neural networks are random functions and ask what distribution they're from, but can you actually do anything with this? And does it buy you anything, right? So I want to give you the simplest example, which is in work due to Neil from the 1990s. I think it was his PhD thesis. So, and concretely, if neural networks are just words to you, I'm literally showing you a function here that is one of the simplest neural networks that is instantiated on computers. So don't worry about this whole thing here. The point is that the neural network is some function, f of x in this case, where it takes x and it multiplies it by a matrix of parameters. These are called the weights, where the parameters are drawn from some distribution. And then it adds a vector called the bias that is drawn from some distribution. It acts with an element-wise nonlinearity on that whole object. Okay? And then again, in what's called the output layer, it acts with this matrix W1, which is another weight matrix with different parameters, and adds a bias vector. So this is called a single layer feed-forward network. And as you can see, this is just a function. Whenever you fire it up on your computer, the parameters in these matrices W1 and W0 and the parameters in these vectors B0 and B1 are drawn from some distribution. The limit that we're interested in to try to understand what distribution these random functions are coming from is the infinite n limit. So the crucial thing I'd like to point out is that this matrix here is a d out, which is the output dimension of the neural network, by n matrix. It takes something from Rn and it maps it down to d out. So as I take n to infinity, the number of parameters in this neural network goes to infinity. And what's happening in the output is that it's adding an infinite number of independently and identically distributed random variables. Crucially, this is the case where the central limit theorem applies. And in particular, what that means is that the output is drawn from a Gaussian. Okay, so punchline, I just gave you the details. This neural network for this architecture in the infinite width limit, this is called when n goes to infinity, it's drawn from a Gaussian process. A Gaussian process is something that doesn't appear in the high energy theory community that well, but you may have heard about it in the context of astrophysics. A Gaussian process for our purposes here is basically just a Gaussian distribution on function space. And that's the distribution that at large n, at infinite n, these neural networks are drawn from. If this was the end of the story, it would not be that exciting because that's not a particularly modern architecture. What we've learned in recent years is that most architectures admit a limit when n goes to infinity, where those neural networks in that architecture are drawn from a Gaussian process. Furthermore, this property, which is crucial to everything I'm saying here, also persists under appropriate types of training that I'm happy to comment on. This isn't just something about randomly initialized neural networks. This Gaussian process property can persist during training. Okay, what does all of this have to do with quantum field theory? We don't normally put it this way, but free field theory is a Gaussian process. If you wanted to describe Euclidean quantum field theory to a statistician, you would start with the free theory. And what you would do is you would write down Feynman's path integral, and you would say, okay, the distribution on functions is e to the minus s for some functional s of phi. And crucially, this s of phi in free theories is Gaussian, which is why we can solve free theories exactly. So infinite neural networks have a deep relationship to free field theory in that they are Gaussian processes. Crucially, the statistics in these cases are entirely determined by the 1-point function, which is the mean of the Gaussian process, and the 2-point function, which is known as the Gaussian process kernel. In the context of quantum field theory, we call the 2-point function the propagator. And these correlate, and furthermore, the fundamental object that one wants to study is the correlation functions of these neural networks, which you can compute in terms of Feynman diagrams, like here. So as always, there's Feynman rules that tell you how the Gaussian process kernel can be written as little widgets, where if you know the map between the widgets and the analytics, you write down correct expressions for the correlation functions. Okay. So what about at finite n? The function space distribution in this case, if it's Gaussian at infinite n, and then you're at large but finite n, what that means is that small non-Gaussianities can creep into the story with the constraint that as n goes to infinity, those non-Gaussianities need to go to 0. In quantum field theory, those non-Gaussianities are the precise analog of particle interactions. We do perturbations around the Gaussian fixed point in quantum field theory. That's basically all of the interactions of the fundamental particles in the standard model are of this type. And so when we're in finite n neural networks away from the infinite limit, but where n is still large, we have weakly coupled interactions appearing in these neural networks arising from the small non-Gaussianities.
Jim, sorry to interrupt. You have 5 more minutes.
5 more minutes total, including questions?
No, plus questions.
Plus question. So questions.
We'll have an extra 5 minutes for questions.
Okay, good. That's perfect. I'm on pace for that.
Okay.
Yeah. Thank you, Babu. So right to arrive at the central point again. In the infinite n limit, neural networks are drawn from Gaussian distributions on function space. Therefore, at finite n, but where n is large, there's small non-Gaussianities that can creep into the picture, which is the analog in quantum field theory or in particle phenomenology of turning on interactions. And so you can try to set up some effective field theory of these neural networks where you have some model that you write down for how the non-Gaussianities appear in the difference between the free action and the interacting action. And there's a whole correspondence that we've built up along these lines in a very detailed story. But in this context, you can again compute Feynman diagrams given some model for the non-Gaussianities. But the central point in some sense is that when I say neural network PHENO, what I mean is that modeling interactions with this delta S, that's what you could do in this framework that I've just set up, and then constraining that delta S with experiments and making new predictions and verifying those predictions, that is, in some sense, in the same way that one does PHENO of particle physics or PHENO of condensed matter systems, that would be PHENO of neural networks, right? And one might hope to do that for state-of-the-art networks. So for example, there's these transformer architectures that have really made a splash in the last 4 years since they arose in 2017. One would love to understand these neural network distributions better. So I say this a little bit, recognizing that to this PHENO community and to myself as a string phenomenologist, the reason that we care about things is that it's the phenomenology of fundamental particle physics and cosmology, right? And that is something that's very different from this. But on the other hand, it would be better to, it would be good to better understand these neural network systems. And if we could do it using this phenomenological approach, it could lead to real breakthroughs in machine learning. So just something concrete to say is that the 1-point function of the trained network distribution, which could have this perturbative description, is the central object in supervised learning. when we do the learning of the type where we're predicting outputs given inputs, the thing that one would really love to know if you were infinitely powerful is what is the one-point function of the trained distribution. And that's something that could have a real impact in computer science. So this other type of phenomenology, while it's not as dear to my heart as the particle physics and cosmology phenomenology that I'm used to and that you're used to, it could really lead to breakthroughs in machine learning. So I think it's exciting. To give you one crisp result before I finish, to prove you can actually do things with this, there's some stuff in the backup slides too. I want to say, what about the symmetries of this distribution? If I'm saying that there's, in essence, a quantum field theory of a given neural network architecture, you'd like to know what are the symmetries of that distribution. So clearly, any neural network phenomenology would benefit from knowledge of the expected symmetries of the distribution. And like in physics, we could use experiments to determine what they are. But there's actually another handle in these systems that allows you to determine the symmetries of the neural network effective action. And that's to use duality. So there's two different ways to compute the correlation functions. The correlation functions is just the expectation value of the neural networks evaluated on some inputs. On one hand, one can compute it if you knew the neural network effective action, which shows up in this PF as e to the minus SF. You could compute these correlation functions in this way, in a fundamental way. But suppose you don't know the neural network effective action. You cannot compute correlation functions for an action that you do not know. On the other hand, if you have another duality frame in which you can compute them, which is the way that ML people normally compute them, you can compute the correlation functions in this duality frame and then use its symmetry properties to deduce the symmetries of the effective action. So this is what we're doing in our upcoming paper. We are using duality to determine the symmetries of neural network effective actions. And just as one concrete thing, there are actual calculations theoretically that you can do in this context. And here's one of them. So what this example shows is that if you have a capital D dimensional output symmetry of a neural network distribution, assuming that you have what's called a linear output layer, and moreover that the weight and bias parameters in there are drawn from SOD invariant distributions, then it turns out that the neural network distribution itself on function space is symmetric. And you show it via a calculation like this. Okay, so once again, I had two main points in this talk. One is that when we consider string phenomenology in 2021, there's many approaches that one might take, and different people have different opinions on this. One concrete way that I like to think about it is if I just draw a vacuum of V from a uniform distribution on everything that we know about string theory to date across all string theory constructions, a universal story that emerges is that there should be many axion-like particles, many gauge sectors, and when the theory is controlled, these are light and weakly coupled. This goes by the broader name of what I like to call string remnants. These are degrees of freedom that arise naturally in string theory that can have important implications for particle physics and cosmology. And they're not there necessarily to solve the bottom-up problem that we have in the standard model of particle physics or cosmology. They're just there coming from the UV construction. So in my view, this complements some of the shifting paradigms that are happening in model building in cosmology and particle physics. And so I have a lot of fun talking about these things with people, and I encourage you, if you're interested, to send me an email or to ask questions. The second thing is neural network phenomenology. The takeaway in this context is that neural networks are random functions from nearly Gaussian distributions. And so you can model those non-Gaussianities with quantum field theory techniques, with effective field theory. And that's a lot like particle phenomenology. So in the same way that we have non-Gaussianities that model particle interactions beyond the standard model, we could write down non-Gaussianities that are attempting to model the statistics of the neural network distribution. And finally, I showed you that there's a duality frame that naturally arises automatically in these machine learning contexts, and you can use it to do useful things like determine the symmetries of the neural network effective actions. Generally, though, I mean, since this is a broad audience, I'd like to just boldly claim that what is happening in computer science is really special. And relative to math and physics, computer science is still in its infancy, just in the sense that math and physics have been playing nicely together for 2,000 years, and especially the last 500 years. But computer science goes back at most sort of 200 years under typical estimations. And concretely, Turing was about 100 years ago, and it's not that long ago that people started getting personal computers. And so this is a new story relative to the way that math and physics get woven together. And I think it's exciting that we're still early in the period of computer science and how it might affect math and physics. So in particular, a lot of our most cherished physics problems are often computationally unwieldy, and we really have new opportunities to use deep learning and other techniques for progress. So for me, that's the string theory landscape, its implications for particle physics and cosmology, and also connections between string theory and math. But this toolbox coming from deep learning is very general, and if you're interested, it's just a great time to dive in. So thanks a lot, and I'll take questions.
Thank you very much, Jim, for a very nice discussion of string phenomenology and deep learning. We do have time for questions. I see there are a few questions already on the Q&A section, so I will go over them. But if you have more questions, please type them in. Let me begin with the chronologically. The first question is the following. A naive question from a non-stringy person on part 1 of your talk. When you say standard models, what exactly are you referring to? Is it some probability distribution of the standard model parameters with one of them matching what we observe, or all of them are the exact replica of the good old standard model we know of? In either case, how can we possibly test your multiple standard models in experiments?
Yeah, so what I mean by standard models in that context is sort of a weak notion that string phenomenologists often mean, which is that we have constructed some minimal supersymmetric version of the standard model prior to taking into account supersymmetry breaking effects. But in that context, you want to use the topology and geometry of the extra dimensions to ask how many particle generations do I have? So in those contexts, we have 10 to the 15 concrete geometries that give rise to SU3 times SU2 times U1 at low energies coming from what's called 7 branes. And those constructions have exactly 3 generations of chiral supermultiplets realizing the exact chiral spectrum of the MSSM. So that's what I mean by standard models. And indeed, to a PHENO community, that's why I put it in quotes, because it's what standard models sort of means in our community, but obviously that's not the full story. As far as experiments, in those cases, it's cases with multiple axion-like particles. In my opinion, the thing to do is not to take those to the bank and try to test those exactly. It's to sort of take the broader lessons and to try to ask what are the lessons that are coming from string theory, and do those affect how we think about particle physics and cosmology? That's what I got at in the second half of the talk.
Thank you. Okay, the second question from Peter Denton. Can you provide any insights on why we find the number of ALPs seems to be preferred to be around 1,000 and not order 1 or not a billion?
Yeah, that's a great question. So the basic statement is that we build up these geometries from some starting point with a low number of ALPs. Yeah. And in particular, we can then do topological transitions to different geometries that connect all of these geometries in one big structure called a moduli space. But crucially, you can't do that forever. This process of adding topological structure to the geometry, which gives you more and more and more ALPs, it doesn't go on forever. It terminates. And in particular, there's a result. The results I quoted are in the context of something called an elliptically fibered Calabi-Yau fourfold. There was a proof in the math community, I think in 2017, due to Dicerbo and Sfaldi, that the number of topological types of those things is actually finite, that it doesn't go on forever. And so we're in this interesting situation where we know that there's at least 10 to the 755 of them, but we also know that it can't go on forever. And so in particular, because the number of ALPs is going up as you build on this topological structure, but we also know that it truncates somewhere, you can't go up to a billion.
Thanks, Jim. Another question from John Wilson. Whenever I hear about Gaussian processes and machine learning, I think of Kriging. Is Kriging at all relevant to the QFT, neutral net Gaussian process relationship that you're discussing?
So I forget precisely what Kriging is. I think it's something that shows up in Bayesian inference. So maybe I'll go on there. I don't know if John can say something quickly about that. But yes. So the simplest version of the story that I said is about neural networks at initialization. But as I alluded to, there are different training schemes that preserve the Gaussian process property during training. And in particular, one way to do it is via what's called the NNGP correspondence, which is recognizing that these neural networks are drawn from Gaussian processes, and you can do standard exact Bayesian inference on Gaussian processes in that structure like you normally would do. And so indeed, what that does is it updates you from one Gaussian process to another trained Gaussian process. And I mean, I would have to remind myself of the definition, but I think kriging shows up in that context. So indeed, you can do exact Bayesian inference on these large N neural networks. And you can also do gradient descent with MSE loss, and that preserves the GP property.
All right, thanks. I have my last question is this. You talked about string remnants.
Yes.
Isn't that going to upset the unification of gauge couplings? And are you worried at all about string couplings being unified?
Yeah, I mean, it definitely can't. I mean, it depends on what the remnants are. If they're uncharged, they're not going to be as much of a problem for unification. But one thing that does show up regularly is vector-like pairs, what I like to call quasi-chiral vector pairs of fermions. It means they're vector-like with respect to the standard model, but chiral with respect to some other symmetry. So there's symmetry reasons that these things might be light, and definitely those can spoil gauge coupling unification. There's a more general question, which is, how seriously should we take gauge coupling unification from a UV perspective? It's something that is arising in low energy data, which of course in the standard model does not exactly unify. It does better in the MSSM. And there's a question from a theoretical perspective, which is how hard would it be to fake gauge coupling unification in string theory? To have a setup where it might naively look like a gut, but it's not actually a gut. And that's an open question and something that I'm working on now.
All right, thank you very much for a clear explanation to all these questions. And I think we are kind of out of time for this session, for this